Overfitting and underfitting describe two fundamental ways AI systems fail to learn effectively. This video explains these concepts intuitively, focusing on how models either learn too much from training data or fail to learn enough to capture meaningful structure. Machine learning aims to extract patterns from data that generalize beyond specific examples. The central challenge is not fitting the past, but performing well on new, unseen situations. Both overfitting and underfitting arise from imbalance. One reflects excessive sensitivity to data, while the other reflects excessive rigidity. Overfitting occurs when a model memorizes training data rather than learning general patterns. It performs well on familiar examples, but poorly on new ones. Underfitting occurs when a model is too simple to capture important structure. It performs poorly even on the data it was trained on. Effective learning lies between these extremes. The goal is sufficient flexibility without memorization. Training performance measures how well a model fits known data. High training accuracy alone is not evidence of good learning. Test performance evaluates generalization. It reflects how models behave in real-world conditions. Overfitted models show a large gap between training and test performance, indicating poor generalization. Underfitted models perform poorly on both training and test data, signaling insufficient learning. Graphically, overfitting appears as overly complex curves, while underfitting appears as overly smooth ones. Model complexity controls expressiveness. Too many parameters increase overfitting risk. High-variance models react strongly to small data changes, capturing noise instead of signal. High-bias models impose strong assumptions that prevent learning meaningful patterns. The bias-variance trade-off reflects this tension. Improving one often worsens the other. Small datasets amplify overfitting because there are fewer examples to constrain learning. Limited diversity further restricts generalization, even when data volume seems sufficient. Noise introduces irrelevant correlations. Overfitted models treat noise as structure. Too many features increase dimensionality, making models sensitive to spurious patterns. Regularization discourages complexity by penalizing large parameter values. Simpler models often generalize better when data is limited or noisy. Cross-validation improves reliability by evaluating performance across multiple data splits. Early stopping halts training before memorization occurs. Training too long encourages overfitting. Too briefly causes underfitting. Model capacity defines how much complexity can be learned. Insufficient capacity prevents learning relevant structure. Excess capacity enables memorization of irrelevant details. A useful analogy is education, memorizing answers versus understanding concepts. Rote learners fail when questions change. Conceptual learners adapt. Smooth trends usually indicate generalization. Jagged curves suggest overfitting. Testing on training data falsely inflates confidence. Data leakage introduces information that would not exist in real use. Feature leakage creates unrealistic performance during evaluation. After deployment, data distributions change, requiring monitoring. Static models degrade as environments evolve. Periodic retraining restores alignment with reality. Overfitting can emerge silently in production. Underfitting produces consistent but limited results. Model selection balances complexity with robustness. Hyperparameters regulate learning behavior. Design choices involve trade-offs shaped by context. No model is universally optimal. Acceptable error depends on application risk. Simpler models are often easier to explain. Overconfidence in metrics hides generalization failures. Human oversight ensures correct interpretation. Learning produces approximations, not truth. Designing for reality means accepting imperfection. Effective models balance learning without extremes. Next, we examine why many AI systems operate as black boxes.